Okay, we're live. Hello everyone. I'm Verdi Arbusto, and this is the Schumann Resonance Harmonics channel on YouTube, Facebook, mainly Facebook. If you're new here, welcome. Remember to like, share, comment, and subscribe. If you've been here for a while, make sure that you're still subscribed and hit the notification bell to all of them. And go to an old video and comment and just say hi. I appreciate that. I appreciate the comments. I like the comments. I read them all. I may not comment. I may not reply to something that you've said. I'm likely just to have hit the thumbs up or the a little heart to let you know I've seen it. Okay. And some things people have written, I'm still trying to process. When people write a post as long as one that I've wrote, it's like, oh wow, I have to actually do some work. And sometimes the work may just be, I'll pray for you. It may not be an answer that I can give, and that's fine. Much love anyway. All right, so in my typical kind of all over the place, skewed up fashion, I have the introduction to this and the other section to this video that talks about solar wind, sunspot, and the other thing, the solar cycle. Okay, so that's the introduction really to this. But so I'm kind of going back and forth, integrating the two of them. And I don't even want to say any more about this. I just want to get into the material because there's a lot of stuff I have to read, and I've done the introduction elsewhere. In addition, this right here, the background is fairly much the same as the other one, and this one is a little bit more important because it's more relevant, but the other one is the background information that is equally as important to know. So that's kind of why I did this odd numbering system of these three first, but the other one gets the introduction. The other one gets the introduction because the other material is shorter. This is long as, this is just long, a lot of information. So the introduction goes on the other one. All right, so we're 2 minutes, 41 seconds into it. All right, so before we get into this, take a break. Have a coffee, I'm not going to stop at the, actually, yeah, there might be a 5-minute mark here. All right. No, this isn't going to be a 5-minute mark. All right, so pause because I need a cup of coffee. Now, roughly speaking, there's another 8 minutes of reading. All right, so CME. What is a coronal mass ejection? Okay, coronal mass ejections, CMEs, are large expulsions of plasma and magnetic field from the sun's corona. They can eject billions of tons of coronal material and carry an embedded magnetic field, frozen in flux, that is stronger than the background solar wind interplanetary magnetic field, IMF strength. Okay, and this IMF strength is measured through the KP index, or the KP index essentially is the measurement of the solar wind interplanetary magnetic field strength that they talk about. CMEs travel outward from the sun at speeds ranging from slower than 250 kilometers per second, km over s, to as fast as near 3,000 kilometers a second, which is fast indeed. The fastest Earth-directed CMEs can reach our planet in as little as 15 to 18 hours. Slower CMEs take several days to arrive. All right, so this corrects me in something that I'd said recently, that a CME can take, it can take several days, but, like maybe 4 or 5. I think I was right when I said that at first, that it, maybe up to 4 days, up to 5, but depending, we tend to get them within 3 days. I didn't think that was off. So, when they're talking about 15 to 18 hours, and you got to remember, a solar flare goes faster. So depending on what's being ejected depends, is what creates how much time it takes. Hopefully that made sense to you. And, I think you can expect that. You can understand that depending on what is being sent out from the sun, it'll vary the time that material, that stuff, arrives. That's just a simple matter of physics. Interplanetary geophysics. All right, back to the material. They expand in size as they propagate away from the sun, and larger CMEs can reach a size comprising nearly a quarter of the space between Earth and the sun by the time it reaches our planet. So it stretches out a lot. It can. The more explosive CMEs generally begin with highly twisted magnetic field structures called flux ropes contained in the sun's lower corona become too stressed and realign into a less tense configuration, a process called magnetic reconnection. And that's something you have to see. Okay, when it twists, and it's like a toroid shape, it kind of twists and turns. This can result in the sudden release of electromagnetic energy in the form of a solar flare, which typically accompanies the explosive acceleration of plasma away from the sun, the CME. These types of CMEs usually take place from areas of the sun with localized fields of strong and stressed magnetic flux, such as active regions associated with sunspot groups. CMEs can also occur from locations where relatively cool and denser plasma is trapped and suspended by magnetic flux extending up to the inner corona, filaments and prominences. Okay? When these flux lines reconfigure, the denser filament or prominence can collapse back to the solar surface and be quietly reabsorbed, or a CME may result. CMEs traveling faster than the background solar wind speed can generate a shock wave. All right, let me read that again. CMEs traveling faster than the background solar wind speed can generate a shock wave. Okay. These shock waves can accelerate charged particles ahead of them, causing increased radiation storm potential or intensity. Important CME parameters used in analysis are size, speed, and direction. These properties are inferred by orbital satellites, coronagraph imagery by SWPC forecasters to determine any Earth impact likelihood. The NASA Space and Heliospheric Observatory, SOHO, carries a coronagraph known as the Large Angle and Spectrometric Coronagraph, which is LASCO. This instrument has two ranges for optical imaging of the sun's corona, C2, which covers distance range of 1.5 to 6 solar radii, and C3, which is a range of 3 to 32 solar radii. The The LASCO instrument is currently the primary means used by forecasters to analyze and categorize CMEs. However, another coronagraph is on the NASA Stereo A spacecraft as an additional source. Imminent CME arrival is first observed by the Deep Space Climate Observatory DISCOVER satellite located in the L1 orbital area. Sudden increases in density, total interplanetary magnetic field IMF strength, and solar wind speed at the DISCOVER spacecraft indicate arrival of the CME-associated interplanetary shock ahead of the magnetic cloud. This can often provide 15 to 60 minutes advanced warning of a shock arrival at Earth, and any possible sudden impulse or sudden storm commencement as registered by Earth-based magnetometers. Important aspects of an arriving CME and its likelihood for causing more intense geomagnetic storming include the strength and direction of the IMF, beginning with shock arrival, followed by arrival and passage of the plasma cloud and frozen in flux magnetic field. More intense levels of geomagnetic storming are favored when the CME enhanced IMF becomes more pronounced and prolonged in a south-directed orientation. Some CMEs show predominantly one direction of the magnetic field during its passage, while most exhibit changing field directions as the CME passes over Earth. Generally, CMEs that impact Earth's magnetosphere will at some point have an IMF orientation that favors generation of geomagnetic storming. Geomagnetic storms are classified using a 5-level NOAA, NOAA, space weather scale. SWPC forecasters discuss analysis and geomagnetic storm potential of CMEs in the forecast direction and predict levels of geomagnetic storming in the 3-day forecast. Okay, 13 minutes. All right. Source, that's NOAA, published February the 2nd, 2021. All right. All right, so good place to pause, take a drink. I need to get out of a breather. Okay, I'm back. All right. I as much as you may need them, I'm pretty sure I need the kind of pause points. Then we can, at least when you're replaying the video, if you do, or if you come in after the live stream or the premiere or whatever, I like putting these kind of waypoints in the, when I remember. I don't always remember, but at least in the video, they're there. All right, so that was the first part. All right, so the next section here, we'll just say it starts at 1331. When I was looking for the references, the material, I found the short answer from NASA, which I was like, well, it does answer the question, but it's like, well, no, my show needs a little more. So I went and found a second source that was a lot more detailed. So I like how this gives the abstract, tells you basically what it is, and then the other one explains a lot more. So, on behalf of, there are those of you who talk to me and have said that you don't have time to watch the whole videos, and some of these are long. And it's not because I repeat myself or ramble on, but there's just a lot of information. In some cases I do ramble on, yes, enough cases I get sidetracked. Yes, that's a thing. All right. So, but even accepting that, you take an hour video, still shrink it down to 40 minutes by my not, from, I'm sorry, by my, not going off topic. So, uh, you know, like there's still a lot. So that's why, like, and the longer videos tend to have a few different sections to them. That's part of it as well. The longer videos cover more information, and so the short videos I'm able to keep short because they're not, they're focused. I was out in the sun the other day. I got, a little mild sunburn on my shoulder. It's, I've been taking this weekend to recover. I just want to say, the sun, it was, Thursday was a brutal day. Wednesday and Thursday, I worked outside. It was rough. Beautiful day to be outside enjoying it if you don't have to work. Anyway, so all right. So the next part start ending at 16:03. All right. So what is a solar flare? So the short answer is basically it's a solar burst is an intense burst of radiation. Solar flare is an intense burst of radiation coming from the release of magnetic energy associated with sunspots. Flares are our solar system's largest explosive events. They are seen as bright areas on the sun, and they can last from minutes to hours. We typically see a solar flare by the photons or light it releases, at most every wavelength of the spectrum. The primary ways we monitor flares are in the X-rays and optical light. Flares are also sites where particles, these would be electrons, protons, and heavier particles, are accelerated. All right, and the source is NASA, editor Holly Zell. Okay, so NASA gives us the short answer, the long answer. Okay, get your popcorn. Okay, pack a lunch, as they say around here in these parts. If you're going to go over 20 minutes, pack a lunch. What's a solar flare? It's the long answer. Solar flare is basically a giant explosion on the surface of our sun, which occurs when magnetic field lines from sunspots tangle and erupt. A solar flare is defined as a sudden, rapid, and intense variation in brightness. A solar flare occurs when magnetic energy that has built up in the solar atmosphere suddenly releases. Material is heated to many millions of degrees in just minutes, and radiation is emitted across virtually the entire electromagnetic spectrum, from radio waves at the long wavelength end, through optical emission to X-rays and gamma rays at the short wavelength end. The amount of energy released is equivalent to millions of nuclear bombs exploding all at the same time. Solar flares are an occurrence. Solar flares are an often occurrence when the sun is active in the years around solar maximum, or like now when she's just getting warmed up. Many solar flares can occur on just one day during this period. Oh, good golly, yes. Around solar minimum, solar flares might occur less than once per week, or less than that, possibly. So, large flares are less frequent than smaller ones. Some, mostly stronger solar flares can launch huge clouds of solar plasma into space, which we call a coronal mass ejection. when a coronal mass ejection arrives at Earth, it can cause a geomagnetic storm and intense auroral displays. The classification of solar flares. Okay, let me get bold and let me make this. Bam. Okay, the classification of solar flares. Solar flares are classified as A, B, C, M, or X, according to the peak flux, and this is in watts per square meter, and that's watts per meter squared, of 1 to 8 angstroms of an angstrom. They abbreviate that with just the A with a little halo over that. The guy, he was like Norwegian or Finnish, somewhere over there. That's why that's the guy's name, angstrom. That's why he gets the thing and the thing, umlaut and the doohickey. X-rays from Earth as measured by XRS instrument on board the GOES-15 satellite, which is in a geostationary orbit over the Pacific Ocean. The table below shows us the different solar flare classes. Okay, and so this one, the little L-shaped one, is less than. Okay, and the one, the angled bracket, they call those, facing to your right, is greater than. So that's how I remembered it when I was in school. The little L was less than. The other one going the other way is greater than. Okay, so this is the little line under that means either equal or greater than. All right, so they're showing you the class. We talk about, this is the table that he's talking about here. All right. So 7 to 9, you see this is the watts per meter squared between 1 and 8 angstrom. Sorry, so that's just what this chart is. It's giving you a relative strength of what you're looking at in the classes. This is giving you technically, how do they figure out the classes of the strength of these here guys? Okay, because you want to know, And I'll make a sidebar comment on this, that a lot of you who follow Wages World and Suspicious and the other ones, a lot of you, the same ones that I do, and you may have even gotten there from me, whatever, gotten there before me, whatever, doesn't matter. They talk a lot about, when we talk about the KP, we talk about a lot of these different aspects of the solar radiance and what it is. There's a lot of technical information to this that potentially you could know, you could find out yourself if you knew where or had the time to dig it up. So that's one of the public services I do in this, is not give you, I give you the learning necessary to understand what the people that read the graphs do, right? Like, I think that's, if you're new here, you may not know that about me or know what this channel is, that I am a specialist on the Schumann resonances and the atmospheric electronics. As good as I am, whatever, you can debate how the quality of my, technical expertise, that's a thing. But, I've given myself to the technical, explanation of the atmospheric electromagnetics. And so, one of the things is I need to help define the terms that are used so that, I myself use these, but not as much as other people. And so as I sit back and my guides tell me what videos I should use and what information and what, kind of interchange and interface between the hardware and the software that I can provide, how to read the data and the information, this is really important too. The manuals, if you don't know where to go to get the information, you can't read the manual. So sometimes it's important that, to go to know where in the library to look for the information. And, if you consider me like the librarian and I'm giving you this information, like I kind of like providing that that kind of service to you as well, that I don't do so much of the reading of the instrumentation as, say, Wages World. They're a common example of the person that we love. But we also know, for example, as suspicious observers, many of you check yourself the weather, Space Weather News, Space Weather Live, spaceweatherlivenews.com, whatever you got. And they have, you watch the KP index, and, other associated space weather, but a lot of you are just getting into this and you don't know what you're really looking at or how to read stuff or what the letter codes mean. There's a lot of that, and myself included. I know briefly what some of it is. So I do this because I want to know. First off, I need to know. I would like to know. And secondly, if I need to know, you guys probably would like to know and should know. And it's important to know where the Schumann resonances kind of end and space weather itself takes over relative to the effects it has on you and your, physiological, makeup, how you're reacting to the physiological effects of the space weather versus the Schumann, just regular Schumann, which isn't bringing you the same physiological stress that this is. Okay. Hopefully that made sense to you. Made sense in my head before I said it. When I was thinking it was all together. When I said it, it's whatever, I don't know. So hopefully you get something out of it. And please, if you don't understand what I said, or if you have a comment, question, suggestion, leave it in the comments. I welcome feedback and questions on what is, and I love the questions and feedback on what was in the actual video. Believe me, it makes me believe this, that it was, worth doing, that it was worth being here. When I get comments on the video that I can, elicit things, makes it worthwhile for being here. So thank you for your comments and your support otherwise. All right. All right. So back to the material. All right. So that was a good place to pause. All right. Just have a cigarette break. All right. Back to the material, onward and upward. Each each X-ray class category is divided into a logarithmic scale from 1 to 9. For example, B1 to B9, comma, C1 to C9, comma, etc. An X2 flare is twice as powerful as an X1 flare and is 4 times more powerful than an M5 flare. The X class category is slightly different and doesn't stop at X9 but continues on. Solar flares of X10 or stronger are sometimes also called super X-class solar flares. Okay, AB class solar flares. The AB class are the lowest class of solar flares. They are very common and not very interesting. Okay, says you. The background flux, which is the amount of radiation emitted when there are no flares, is often in the B range during solar maximum and the A range during solar minimum. Okay? C-class solar flares. C-class solar flares are minor solar flares that have little to no effect on Earth. Only C-class solar flares, which are long in duration, might produce a coronal mass ejection, but they are usually slow, weak, and rarely cause a significant geomagnetic disturbance here on Earth. The background flux, which is the amount of radiation emitted when there are no flares, can be in the lower C-class range when a complex sunspot region inhabits the Earth-facing solar disk. Okay, M-class solar flares. M-class solar flares are what we call the medium-large solar flares. They cause small R1 to moderate R2 radio blackouts on the daylight side of Earth. Some eruptive M-class solar flares can also cause solar radiation storms. Strong, long-duration M-class solar flares are likely candidates to launch a coronal mass ejection. Okay. It's late here and I should be sleeping. But I love you, so let's go on. If the solar flare takes place near the center of the Earth-facing solar disk and launches a coronal mass ejection toward our planet, there is a high probability that the resulting geomagnetic storm is going to be strong enough for aurora on the middle latitudes. Okay? Aurora on the middle latitudes. X-class solar flares. X-class solar flares. X-class solar flares are the biggest and strongest of them all. On average, solar flares of this magnitude occur about 10 times a year and are more common during solar maximum than solar minimum. Strong to extreme, R3 to R5, radio blackouts occur on the daylight side of the Earth during solar flare. If the solar flare is eruptive and takes place near the center of the Earth-facing solar disk, it could cause a strong and long-lasting solar radiation storm and release a significant coronal mass ejection that can cause severe G4 to extreme G5 geomagnetic storming on Earth. Okay, let's pause here for a moment. Okay, so what's above an X9? All right. The X class continues after X9 instead of getting a new letter, and these solar flares are often referred to as super X-class solar flares. Part of me would like to know why or how they come up with a rationalization to figure out how they figure out the lettering and numbering system of these things. Why can't y'all keep it consistent so we can follow along? Just wondering. I don't know. I'm just wondering. Solar flares that reach or even surpass the X10 class are, however, very rare and occur only a few times during a solar cycle. It is actually a good thing that these powerful solar flares do not occur so often, as the consequences on Earth could be severe. Amen, brother. The coronal mass ejections, which can be launched by such solar flares, are known to be able to cause issues with our modern technology like satellites and power lines and your unshielded electronics. Yep. One thing to note with Super X-class flares is that an X20 solar flare is not 10 times as strong as an X10 solar flare. Okay. An X10 solar flare equals an X-ray flux of 0.001 watts per meter squared, while a X20 solar flare equals 0.002 watts per meter squared in the 1 to 8 angstrom wavelength. Okay. So that's actually 1,000th stronger. 1/1000th stronger. All right. That's your tens, hundreds, thousandths place. Okay? The largest solar flare ever recorded since satellites started to measure them in 1976 was estimated to be an X-28 solar flare, which occurred on November 4th, 2003 during solar cycle 23. The XRS long channel on the GOES 12 satellite was saturated at X17 for 12 minutes by the intense radiation. A later analysis of the available data yield an estimated peak flux of X28. However, there are scientists who think that this solar flare was even stronger than X28. Okay, a good thing for us was that the sunspot group, which produced this solar flare, had already rotated largely off, it says off, but it should say off, the Earth-facing solar disk when the X28 solar flare occurred. All right, so for those of you who are following along and who remember just within the last 48 hours, 28 to 48 hours of when I'm recording this, there was a huge CME flare and CME. It had been flaring. It flared for a little while, and then as it turned the limb, it shot out, and we are supposed to be getting a glancing blow from that within the next 24 to 48 hours. So we're going to see what happens with that. But that's what he's talking about, the same exact thing in the X28. Like, I don't know what the size of this thing that just left Earth, but it's got to be close to that. Like, I don't know how you measure that, right? I'm not the one measuring it, but I'm like, it's huge. I think it was huge. Massive. If that thing hit Earth, oh my. Yeah. All right. So just a note, side note. A thing to note is that there has not been a solar flare that saturated the XRS channels on GOES 15 as of March 2017, but it is expected that it will saturate about the same flux levels. Okay? All right, high frequency HF radio blackouts caused by solar flares. Bursts of X-ray and extreme ultraviolet radiation, which are emitted during solar flares and can cause problems with HF, high-frequency radio transmissions, on the sunlight side of the Earth, and are most intense at locations where the sun is directly overhead. All right, that's good to remember. It is mostly high-frequency HF, and that's 3 to 30 megahertz radio communication that is affected during such events, although fading and diminished reception may spill over to very high frequency VHF, and that's 30 to 300 megahertz and higher frequencies. These blackouts are a result of enhanced electron densities in the lower atmosphere, D layer, during a solar flare, which causes a large increase in the amount of energy radio waves lose when it passes through this layer. This process prevents the radio waves from reaching the much higher E or F1 and F2 layers, where these radio signals normally refract and bounce back to Earth. Radio blackouts caused by solar flares are the most common space weather events to affect Earth, and also the fastest to affect us. Minor events occur about 2,000 times each solar cycle. The electromagnetic emission produced during flares travels at the speed of light, taking just over 8 minutes to travel from the Sun to Earth. These type of radio blackouts can last from several minutes to several hours, depending on the location of the solar flare. How severe a radio blackout is depends on the strength of the solar flare. The highest affected frequency, HAF, during an X-ray radio blackout during local noon is based on the current X-ray flux value between the 1 to 8 angstrom. The highest affected frequency, HAF, can be derived by a formula. Below, you will find a formula where you can see the HAF during a specific X-ray class. Right. So this right here, you can kind of study it, but they're giving you GEO's X-ray class and flux, the M1, M5, X1, X5, and these are, you see, the higher up it goes, the higher the frequencies are they're affected, and these are radio transmissions. All right. The R scale. All right. Good place to take a pause. Let me, 41 minutes. Holy crap. I need a refreshing beverage, so let's pause here. Okay. The R scale. NOAA uses a 5-level system called the R scale to indicate the severity of an X-ray related radio blackout. This scale ranges from R1 for a minor radio blackout event to R5 for an extreme radio blackout event, with R1 being the lowest level and R5 being the highest level. Every R level has a certain X-ray brightness associated with it. This ranges from R1 for an X-ray flux of M1 to R5 for an X-ray flux of X20. On Twitter, we provide alerts as soon as certain radio blackout thresholds has been reached. Okay, and this is Space Weather Live, that link. Because each blackout level represents a certain GOES X-ray brightness, you can associate these alerts directly with a solar flare that is occurring at the moment. We can define the following radio blackout classes. All right, and so I'm not sure if you can see, but over here you have, this is a screen capture I did from their website. So the link is below. So if you go there, you can see it a little better than this. This is theirs. You got to go to it and see it there yourself. But they're giving you the R scale R1. This line is R2, R3, R4, R5. And then you're giving you the X-ray threshold according to M1. This is M5, X1, X10, X30, it looks like. And so then this is the average frequency, 2,000 per cycle. All right, I can't really read that there, but you got to go there and you figure it out. I'm not even sure what it is that I'm really exactly looking at, but if you do radio, and you rely on radio signals in your business, your industry, this is something that you'll want to take care of or concern with in the next couple days, because and here, as we're coming into the solar maximum, we're going to be getting more of this. You need to be prepared, and you need to know. All right, so this is the end of this information. So this is definitely over an hour's worth of material between the two of these. So I think I'm going to post the other one first because it's shorter. And then I'm going to post this one in some way, Premiere or whatever, the video. Anyway, I'll figure it out. All right. I still got to figure out what my thumbnail is going to be for this. I have no idea. I'll have to find an image of the burst of some kind of burst of the sun. All right. So anyway, all right. So enough. Thank you all for being here. I appreciate very much the love, the comment, and the support. I just thank you. The wonderful comments from people make this worth being here, and it makes it worth it. Thank you all. Good night.